And welcome back to another exciting episode. Again, we are on Activity 9. More importantly, we're on Lesson 9-3, Reflections. Right? Activity 9 is all about transformations. We learned what a rigid motion or a non-rigid motion was in Lesson 9.1. Lesson 9.2, we uncovered the first rigid motion, which was a translation. And now we are looking at our second rigid motion, the reflection. So let's get after it. Let's take a look at our learning targets. Let's annotate those. We are going to we're going to put on a show, we're going to perform reflections on and off the coordinate plane. On the last lesson, we looked at GeoGebra, exploring those translations off the coordinate plane, saw some characteristics that we actually saw also on the coordinate plane. So we're going to do that here as well. We're going to perform reflections on and off the coordinate plane. Then we are going to identify reflectional symmetry in plane figures. So that's actually one of your vocab words, reflectional symmetry. So hopefully you've been studying up on that as we'll see it in this lesson. So again, Mr. Scott plans another transformation for the marching Cougars. The sign of the y coordinate of each marcher changes from positive to negative. From positive to negative. Maria, whose position is shown by the X in the diagram, moves from 2, 4 to 2, negative 4. So if you would, take a chance to continue reading through this text, looking at the diagram, and then complete the chart or the table on number 1. Again, draw a line at the bottom of the page, work all the way to that line, then play the video to see how you did. Okay, hopefully you've taken a second to digest some of this information here. I've highlighted some very important parts of this text, as well as completing the table. If you completed the table correctly, you really just practice in this first column here. This function represents a reflection across the x-axis. So you took all these pre-image points, 1, 10, 6, 10, 1, 2, and 6, 2, and essentially reflected those across the x-axis where we have these image points. And then the second column was performing a reflection across the y-axis, and you have these image points as a result. So if you notice, take a look over here. These are kind of what the functions look like for translations, pretty basic. X plus A, Y plus B, where A and B could be positive or negative depending on if we move left or right or if we moved up or down. And you notice the complexity kind of builds a little bit here with reflections. And a couple things I'd like to point out to students, the way it's easier to think about these reflections instead of trying to memorize them as these functions are written, is, for example, every point, x, y, goes to negative x comma y. When you reflect across the y-axis, the x value changes. For example, up here on our coordinate plane, if I was located at 1, 8, and I reflect across the, what were we talking about, the y-axis, if I reflect across the y-axis right here, my x value changes. It literally goes just on the other side of that y-axis. So notice my y value is still the same, but my x value changed signs. So when you reflect across the y-axis, the x changes. And likewise, for the second function here, when you reflect across the x-axis, the y value changes, so the y coordinate changes. And that's what we saw here. We saw that Maria went from 2, positive 4, which is here on the coordinate plane, to 2, negative 4, which is here on the coordinate plane. And so they still have the same x value, positive 2, but the y value changed signs because when you reflect across the x-axis, the y coordinate changes. And the last function we see here is a reflection across the line y equals x. Every point, or every x and y, literally swaps. And so I wanted to show you that line. A lot of students are unfamiliar with the line y equals x. So I wanted to take a second and show you that on my other screen here. So let's take a look. So the line y equals x, a couple things, that's a linear equation. It's the most basic linear equation this is, where the slope of our line is an understood 1 Remember, the slope is the coefficient found in front of x. So m here is positive 1, or 1 over 1. And the y-intercept, you notice you don't see anything written out here next to the x, so we can assume the y-intercept is 0. So that tells us this line, the y-intercept is 0, so it crosses through the origin and has a slope of 1 over 1. So we go up 1, right 1, up 1, right 1, up 1, right 1, or the exact opposite, down 1, left 1. And this is what the line y equals x looks like. Not too shabby. So reflecting across that line, the function tells us that we literally just swap our x and y. And the way I like to think about it, or it helps me remember this, is that y and x are the same value here. This literally says y equals x and x equals y. So the way I memorize this reflection function is that I know that y and x are going to be the same value, and so I can swap them. So if that helps you remember how to perform that reflection, go for it. So we're starting to see how a reflection alters a figure. Notice that this rectangle, this marching cougar's rectangle, is still the same size and shape after the transformation. So that lets us know it is in fact a rigid motion. And a couple things I also want to point out is the reflection across the x-axis here. Let's point something out. I'm going to draw where it would have ended up if it was all on the same coordinate plane. So this is what it looked like. The reason I'm just doing this is I want to kind of point something out to you, and Maria would have ended up right here. A reflection across the x-axis, or any line of reflection, because that's what they refer to here. Every reflection has a line of reflection. However far a point is in the pre-image, however far it is from the line of reflection, that's how far it ends up on the other side of the line of reflection. For example, Maria was located 1, 2, 3, 4 units away from the line of reflection, and after the reflection, she is still 1, 2, 3, 4 units away. So that's something we can start noticing here. Not only is it a rigid motion, but these points are staying the exact distant or equidistant from the line of reflection, from their pre-image to the image. So let's kind of keep that in our mind as we move on to number 2. So if you would, go ahead and draw a line under number 3. Work through items 2A, B, and number 3 before playing through the video. So on item 2, A and B, you're supposed to predict, hopefully you did that, predict the direction of the arrow after these reflections. So a reflection across the x-axis, this would take this pre-image arrow pointing downward. And then a reflection across the y-axis, if we took that same pre-image arrow and reflected across the y-axis, it should still be facing up. Because remember, a reflection across the x-axis, the y changes, which is actually our axis that runs up and down. So that's another way you can think about it. When we reflect across the x-axis, we're moving really up or down. And then here, a reflection across the y-axis, the x changes. So we're really moving left or right when we reflect across the y-axis. So the arrow on item B shouldn't have changed direction at all. And then it said draw the 2 reflections and were your predictions correct? Now we could easily just draw these reflections, just kind of bypass all this and really not try to notice anything. But I want us to start pulling out important information that's going to help us predict what these reflections are going to do to our pre-images. So one thing I want to point out is we have this tip of the arrow located at 410. And after the first reflection across the x-axis, the pre-image, that tip is located 10 units from the line of reflection. This grid, every square is 2 units. So this point is located 10 units, 2, 4, 6, 8, 10 units from the line of reflection. And so make sure when you reflect across the x-axis that tip of the arrow is still 10 units away from the line of reflection. And likewise, across the y-axis here, the tip of the arrow was located 4 units away from the line of reflection, so it should still be 4 units on the other side of the line of reflection. So don't just draw these figures willy-nilly. There's a reason that we're seeing these characteristics of these reflections, specifically for the x-axis and the y-axis. Now let's take a look at item 4. Go and draw a line under item 4. Take a second to think through that one. This one's pretty intriguing here. And I would also like for you to figure out if you can figure out the line of reflection, the equation of the line of reflection. So take this one a little bit further. It says what reflection maps the arrow to a downward arrow so that also has the tip still at point 410. So I want you to do two things. Figure out what the reflection would look like, and then figure out the line of reflection on this one. So hopefully you took a second to try to figure this one out. This one might be a little difficult, especially if you don't remember equations of horizontal lines. So it said reflection maps the arrow to a downward arrow, so that also has its tip still at the point 410. And I actually said this right here. It might just look like I'm telling you a number, y equals 10, but that's actually an equation of a line where y equals 10. So let's take a look up at our coordinate plane here. So the line y equals 10 literally is a horizontal line at every single point on the coordinate plane where y equals 10. X changes all day long on this line, left, right, positive, negative, but y is a constant value here. It's the number 10. So if I actually reflected this arrow across this line, y equals 10, my point would still remain at 410. What we're learning here, and hopefully we're pulling out here, is that points on the line of reflection do not move. So we might need to add that pretty key point here. Points on the, I'm going to write LOR, not Lord of the Rings, line of reflection, do not move. The book uses the term maps to itself. It literally remains in the same location. Of course, it's following the reflection rule. It's just not going anywhere. Well, if we think about it in that term, however far a point is from the line of reflection, that's how far it has to be after the reflection. So if there is a point on the line of reflection, it's technically a distance of 0 to the line of reflection. So that's why it appears to not move, or in this case, how we got the arrow, the tip of the arrow, to remain at 410. It's the line y equals 10. So I want to take another second here, especially if we're not comfortable with these linear equations like y equals x and y equals 10, take another look at this coordinate plane and kind of explain what that looks like. So all horizontal lines, those are lines that run completely east to west or left to right. They will have the equation y equals some number. In fact, here, let's say, for example, y equals 1. And so every coordinate on this line, y is the same value. Think about it. Here, the coordinate is 1, 1. Here, the coordinate is 2, 1. Here, the coordinate is 3, 1. Here, the coordinate is 4, 1, and so forth. So this is actually the equation, the linear equation, y equals 1. And again, likewise, it works the same way in our negatives. Let's say this is 1, 2, 3. This is negative 3 on our y-axis. So every single point on this line, y is a constant, negative 3. So that's how horizontal lines work, which is kind of backwards in our mind because we think of the horizontal axis, the x-axis, and yet we're saying that the lines are y equals some number when they're horizontal lines. So hopefully you think that the same is true for lines that are vertical. So let's discuss vertical lines. It's the exact opposite. Vertical lines are lines that are directed straight up and straight down, if you want to think about it that way. And those lines always have the equation x equals some number. For example, right here on the x-axis, x equals negative 2. And likewise, at this coordinate, x is still negative 2. Y changed to 1, but x is still negative 2. And likewise, x is still negative 2 here, y is positive 2, but x is still negative 2. And so every single point on this line, x equals the same number. X equals -2. And likewise, I probably said that quite a bit in this video, on the positive side of the x-axis, we see that a line, let's say, for example, at 1, 2, 3, 4, 5, every single point on this line, x equals the same value, x equals 5. So we don't just have to perform reflections across the x-axis or the y-axis or even the line y equals x, which is the white line here. We can also perform reflections across these other lines. Again, all a reflection has to have is a line of reflection, and there are tons of lines on the coordinate plane. And here are a couple ways to identify them. If you see a linear equation y equals some number, it's a horizontal line. And if you see a linear equation x equals some number, it's a vertical line. So keep that in mind as we push forward with our reflections. So let's hop back over here. Number 5 says, could a reflection map the arrow so it points to the right or to the left? If yes, describe the line of reflection. So go and draw a line here, take pun intended. Draw a line here. Think about this. Could a reflection, a flip, map the arrow so that it points to the right or the left? We've explored a couple here that will either force the arrow to point down or continue to point up. But is there a reflection that can make the arrow point right or left? So take a second to think through that one before continuing with the video. So you might have been puzzled with this one for a little bit. Could a reflection map the arrow so that it points to the right or to the left, i.e. parallel? I liked how they said that, parallel to the x-axis. If yes, describe the line of reflection. So this is where they're bringing that function from the previous page to light. You actually can reflect this arrow so that it points right to the left. It's actually using the line of reflection, y equals x. So I wanted to give you an example here of what that looked like. So I redrew an arrow pointing up, and so I have all the coordinates to the vertices of that arrow for 0, 2, 0, 4, -1, 4, 1, 6, I believe that's 3, 4, 2, 4, and 2, 2. So those are the coordinates of the pre-image here listed on the left. And then the reflection across the line y equals x, we're literally following this function. Every point, the coordinates will essentially swap. And so a reflection across that line, 0, 2 went to 2, 0, which is right here. And 0, 4 went to 4, 0, which is right here. -1, 4, 1, 6, and so forth. And I highlighted this point here, the point that's actually on the line of reflection, which is 2, 2, actually didn't go anywhere. And it makes sense because if we're swapping y and x and y are already the same value, it's still 2, 2. But it's again drawing this other point that points, pun intended, points on the line of reflection do not move. So yes, you could actually reflect an arrow. And hopefully you're thinking if it was facing down that more than likely it would then face left after a reflection across the line y equals x. So this is how you're applying this function, a reflection across the line y equals x. Now let's take a gander, moving right along, looking at another reflection. Mr. Scott arranges the tuba players in an arrow formation shown below. Then the tuba player undergoes a reflection that is described by this function, which looks a little bit different. But after you take a second to draw that reflection and answer some of the questions, I want to see if we can maybe simplify the way this function looks and maybe look at it a slightly different way. So if you would, let's see, let's go all the way through the bottom of the page to number 9. So draw a line at the bottom of the page. And when you get to number 9, play through the video to see how you did. So hopefully you took a second to work through this a little bit. We're seeing a different kind of function here. But again, I'll explain that and hopefully make some sense of it, maybe a different way to look at it. Here is my function table. I thought it'd be best, especially with this subtraction here, 8 minus x, that we actually use the table if needed. So all of these points are my pre-image points from the arrow that was given to us. And all of these points are where those points map to after the reflection. So to use this function, 8 minus x, we're going to take 8 and subtract 0. Well, 8 minus 0 is still 8, and the y does not change. For example, here, 2, 4. 8 take away 2 is 6, and the 4 does not change. That's what the function's telling us. So take a second, look at this function table, make sure you did it correctly. And then it says identify the line of reflection. And so we're talking about equations of lines. So hopefully you figured out it was this line right here, which x is a constant value on this line. X will equal 4. That's what we were talking about on the previous slide. Vertical lines have an equation of x equals some number. So in this case, the line of reflection is x equals 4. Number 7 says, which tuba players travel the longest distance during the reflection? Identify the distance. So to help you, what we're learning is however far a point is from the line of reflection, that's how far it travels. So I said tuba players furthest from the line of reflection. Those on this back end of the arrow actually travel the furthest, because however far they are from the line of reflection, that's how far they have to travel after the reflection. And I said that distance was, in fact, 8 units. Then it says, which tuba player does not travel any distance during the reflection? And I said tuba player 4, 5, located at 4, 5, because he's on the line of reflection. Notice we're seeing this similarity over and over again. And again, it all comes back to however far a point is from the line of reflection, that's how far they travel, which leads us to number 9. Explain why the reflection does not change the distance between any given tuba player and the point 4, 5. Well, I said a reflection preserves the size and shape of the figure, i.e. a rigid motion. However far points are from the line of reflection, and in this case 4, 5, because it's on the line of reflection, that's how far they will remain after the reflection. A reflection is a rigid motion, so it's going to preserve that size or shape. So however far a point is from specifically 4, 5, because it's on the LOR, however far it is from that point, it's going to remain that same distance on the other side. Hopefully we're seeing those similarities. Now we're going to transition off the coordinate plane a little bit to see how those same characteristics are remaining true. So number 10 says use geometry software to explore reflections. First, use the software to draw a pentagon, which is a 5-sided polygon. Then draw a line of reflection that passes through one side. That's important. So the line of reflection is actually going to be on the pentagon itself, so one side of the pentagon, and use the software to reflect the pentagon over this line of reflection. So what we're going to do is we're going to transition back over to GeoGebra, and then use GeoGebra. You see it's a very similar figure. We're going to use GeoGebra to perform that reflection across one of the sides of the pentagon. So for those wanting to do it along at home on GeoGebra, you just click on Polygon here, and you can just start drawing it. You don't necessarily have to draw it the exact same way I did, but a pentagon is a 5-sided figure. So you can just add points, it'll draw them, and that's a quadrilateral, not a pentagon. But if you want to draw a polygon, go for it. Once you have that polygon, then you can just draw a line so that it's on one side of that figure. And now that we have this, we are going to go ahead and reflect this pentagon across that line of reflection on side AE. So we're going to go to More, and then we will scroll down until we see our Transform section. So we're going to reflect across or about a line, not a point, although we could reflect about a point. We're going to reflect about a line. So it tells us to select the pentagon first, then select the line. So I'm going to choose 2 points on that line. And here we see an image pop up. Remember, we learned what these little apostrophes mean. It lets us know where those points map to, because it's still point A, it's still point B, but this is where it's located after the reflection or after the rigid motion. So take a second to study the image here. In fact, it is called an image. Remember, the figure after the transformation is in fact called an image. Just to kind of show you that it is a rigid motion, I'm going to go ahead and measure a couple things. So I'm going to find the distance from A to B. Oh, that gave me the perimeter. So the distance from B to A is 2.4. So from A prime to B prime should also be 2.4. And we see, so the the distance is preserved between these points because it is in fact a rigid motion. So let's turn back to our page here and see what kind of questions they have for us. So number 11 says, what happens under this reflection to points that lie on the line of reflection? Well, hopefully you notice here they didn't go anywhere. In fact, when I try to measure A prime, B prime, it still registered it as A. So AE, which was on the line of reflection, actually did not move at all. So let's go back and add that answer. So I said these points, in fact, do not move, or we could say that they map to themselves. The pre-image and image points are in the same location. So then 12 really wants us to start studying this line of reflection. That's what we're doing here. We're studying what happens to points on the line of reflection and points not on the line of reflection. So A says measure the distance of a point to the line of reflection, then measure the distance of the point's image to the line of reflection. So we're using what's called corresponding points. I think I misspelled that. Let me back up. I think it's 2 R's. Corresponding points. For example, when we find the distance from A or B to the line of reflection, then we would use B prime to the line of reflection. Those are considered corresponding points here. And so they ask us to measure the distance from that point to the line of reflection and its image to the line of reflection. And then part B says, draw the segment that connects a point and its image. How is this segment related to the line of reflection? So let's pop back over to GeoGebra. Again, what we've already done is we found the distance from B to A, and from B prime to A or A prime is preserved. It's 2.4. But then they wanted us to draw or find the distance between a point and the line of reflection and the point's image to the line of reflection. So what we're going to do is we're going to draw a line from point B through B prime, map a point on the line of reflection, and then find that distance. So I'm going to do that very quickly for you here. I've actually already drawn the line, plotted point F, and then now I'm going to find the distance from B to F and then from B prime to F prime to see what really is going on. So I found the distance from B to F, 1.9, or B to the line of reflection is 1.9. And hopefully you're starting to digest or assume that from B prime to F will also be 1.9. And we see that is in fact true. So let's go back and answer that question before we look at item B. So I said a point and its image, or I use this new term here to make us sound smarter than we really are. They are equidistant to the line of reflection, or in other words, equal distance. We saw over here that from a point B to the line of reflection was 1.9, and from its image to the line of reflection is also 1.9. So they're equidistant to the line of reflection. Then part B says, draw the segment, we've actually already done that connects a point and its image. How is this segment related to the line of reflection? This actually goes back to something we learned a little bit in lesson 7-3. A couple things we see here is there's a reason that this point from B to F is 1.9 and also from B prime to F is 1.9. We could actually say that these two segments from B to F and from B prime to F are congruent. Well, not only are these two segments congruent, but what we're seeing here is that this line that connects these corresponding points, B and B prime, it is also perpendicular to the line of reflection. So this line of reflection, remember that passed through point A and E, we see that when we connect those points, those corresponding points, B to B prime, that we actually have what's known as a perpendicular bisector. It creates two different things. It creates two congruent segments. We saw that with BF and B prime F. And it also creates right angles with that newly drawn segment. So let's go back and add that to our textbook on item B. So I added the note, the newly drawn segment that connects, again, they're called corresponding points. A point and its image are called corresponding points. The segment is the perpendicular bisector to the line of reflection. Hopefully you're seeing why that is. And you could go back to those figures drawn on the coordinate plane and kind of see how, yes, even points on the line of, points on the coordinate plane and their image creates a perpendicular bisector to the line of reflection. Now let's continue on. We're going to pull away just a little bit even further from the coordinate plane. So it says, like other transformations, reflections can be defined independently of the coordinate plane. That's what we're doing here. We're just trying to study the characteristics of reflections on and off the coordinate plane. If you would, go ahead and draw a line below item B. Take a second, read through the text, and if you can, attempt to draw line L, the line of reflection, that would map this pentagon onto this other one. So take a second, try to complete, try to comprehend before playing through the video. Okay, so hopefully you took a second to try and draw the line of reflection. And I, in fact, forgot to label this as the line of reflection, L. But let's digest a couple things that they're really trying to help us as we understand what a reflection does or is. So a reflection is a transformation that maps any point to its image across a line. So reflections require a line of reflection, such that these two things are very, very important. If P is not on the line of reflection, so if some point is not on the line of reflection, then L is the perpendicular bisector of segment P prime. So I demonstrate that over here. Assuming that P is not on the line of reflection, then the line of reflection is a perpendicular bisector to this segment, such that two things are true. This segment from P to the line of reflection is congruent from the line of reflection to P prime. These two segments are congruent. That's what the term bisector means. Also, it told us that it's the perpendicular bisector, so the line of reflection is also perpendicular to the segment that connects a point and its image. That's if the point is not on the line of reflection. However, if P is, or if some point is on the line of reflection, then P equals P prime. Or in other words, and I drew it down here, if a point is on the line of reflection, it doesn't move. P and P prime are actually located in the same location, because however far a point is from the line of reflection, that's how far it must remain after the reflection. So hopefully you're getting those two key characteristics regardless if we're on or off the coordinate plane. Now, to describe reflections, we will use this notation. We explained that with our translations. We saw something very similar. Here, the lowercase r. So the lowercase r stands for reflection, obviously. The little l here is, in this case, the name of our line of reflection. And just like the notation before, the P in parentheses represents the pre-image point. And what's after the equal sign is the result of the reflection of a point P over the line of reflection L, and it's P prime, our image point. So again, that's what the notation means. We're just starting to understand and appreciate the notation, and we only see this notation when it's off the coordinate plane. Think about it, we see those functions, we see the functions to help us when we're on the coordinate plane, and we see this notation to let us know what's happening when we're off the coordinate plane. So A told us to draw line L, our line of reflection, and then it said label the points, the reflection of A across the line of reflection L, and the result is A prime. So they're really just letting us know, and so forth with B prime. They're just letting us know to label our vertices. So to give you an idea how I drew line L, first thing I did was I drew a segment that connected B to B prime, those corresponding points. Then I knew that because these points weren't necessarily on the line of reflection, that however far B was from B prime, I just went half that distance because it's bisected, and I drew line L such that two things were true, and it's these two things here. That the distance from B to the line of reflection was congruent to B prime to the line of reflection, and, let's use another color, and line L was also perpendicular to that segment. That's why they're telling us back here, if P is not on the line of reflection, then L is the perpendicular bisector of P prime. Or in this case, line L is the perpendicular bisector of B prime. And so that's how I did it. So hopefully you can see that reflection across this line L, where A is mapped to A prime, E is mapped all the way over here. And that makes sense because E is actually the furthest point from the line of reflection, so it should have traveled the furthest after the reflection. D maps to D prime and C maps to C prime. So hopefully you're gaining a sense of how this line of reflection really works. And again, all these things work on the coordinate plane as well as off the coordinate plane. So let's dive on forward. If you would, draw a line below B and answer items 14A through B before playing through the video. So item 14 is a great segue into our next page on page 117. We're seeing something interesting here. They're telling us that quadrilateral ABDC was constructed, and I actually crossed through scalene triangle. It definitely looks more like an isosceles triangle. We don't necessarily assume those things, but this is what an isosceles triangle is. It's where two sides of the triangle is in fact congruent. A scalene, let me write that, isosceles. And scalene is where no sides of the triangle are congruent. So typically you see something like this, where none of the sides are in fact congruent. It just doesn't look that way. ABC definitely looks like an isosceles triangle. Isosceles. So that's why I kind of modified that, but that shouldn't mess you up too much. But they're telling us that this quadrilateral ABDC was actually created by reflecting a triangle across one of its sides. In fact, across line BC. That's why I said over here, line segment BC is the line of reflection. So point P is the intersection of BC, the line of reflection, and line segment AD. So A said, prove that line segment BC is perpendicular to line segment AD. And I said if point A maps to point D, and that's what we know about a reflection, that if line segment BC is the line of reflection, however far point A is from P, that's how far it will be mapped to on the other side. So if point A does in fact map to point D, such that line segment BC is the LOR, then line segment AD has to be perpendicular. It has to be perpendicular to BC, because the line of reflection is the perpendicular bisector of corresponding points in reflection. So if A really does map to D, and line segment BC is the line of reflection, then of course these 2 points, these corresponding points, that segment is perpendicular to the line of reflection. That's what we learned way back up here. So that's using the perpendicular aspect of it. Then part B then says, why is AB, the length of AB, equal to BD? So AB, we know that point A, like we said in A, point A maps to point D. So however far A is from B on the line of reflection, then D has to remain that same distance on the other side of the line of reflection. In fact, D is the image of A, and reflections are rigid motions. Therefore, the length of AB is equal to BD. And I really wanted to emphasize this. Distance is preserved. In a reflection, because it's a rigid motion, the size and shape does not change. So we're seeing how creating quadrilaterals or creating new shapes can actually be done by reflecting a shape across one of its sides. That's what we're looking at here. So now let's see how that ties into our next segment about reflectional symmetry and lines of symmetry. So if you would, draw a line, pun intended, draw a line above 16, read the text, and then complete item 15 before playing through the video. So the next thing we're learning about is something called reflectional symmetry. And now we're giving this line that we've been calling the line of reflection, we're kind of giving it a new name called the line of symmetry. And it all depends on whether or not we're talking about within a figure or outside of a figure. But let's talk about the perpendicular bisector theorem. This theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And the converse is true. The converse for a lot of these theorems are true. If a point is equidistant from 2 points, such like A and B, then it must lie on the perpendicular bisector of line segment AB. So let's go back and say that here. The perpendicular bisector theorem. It says that the theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So this point P being on the perpendicular bisector, in this case, line segment BC, then P is equidistant from point A and point D. That's in fact what we were speaking on primarily in item A. And so we're seeing how this works with reflections, and now we're turning the page literally and seeing how it works in reflectional symmetry. So look again at quadrilateral ABDC. It was constructed by a reflection of a figure. And what that tells us, if you can create a figure by reflecting half of it across one of its sides, then that figure has reflectional symmetry. That's one of our vocab words. Line segment BC in item 14 was the line of symmetry. If I could cut out this quadrilateral, I could fold this triangle ABC, I could fold it along BC so that this triangle would map perfectly onto triangle BDC. And that lets us know, if we can fold it perfectly across that line, that it does in fact have reflectional symmetry, and that line is the line of symmetry. So it says a line of symmetry can be an actual line in the figure, or it may be imaginary, like the ones below. Above, this was an actual line of symmetry that was drawn for us. Now we're having to imagine the lines of symmetry. A figure may have any number of lines of symmetry, including an infinite number. In fact, check your understanding on the next page, you'll see that one of those figures has an infinite number of lines of symmetry. So item 15, you were to draw all the lines. And remember, you can only draw a line of symmetry if one half would map perfectly onto the other. So with this triangle here, it's safe to assume it's isosceles, although we could, in fact, measure it if we had to. But we're suggesting if this is the line of symmetry, this purple line here, that this side maps perfectly onto this side, or they're congruent. And this half maps perfectly onto that half. That's what we're suggesting here with the line of symmetry. So hopefully you're seeing how this ties in with the line of reflection. Likewise, on this triangle here, I put these congruency marks. That's letting us know that this side right here is congruent to this side of the rectangle, and this side is congruent to that side of the rectangle. So that's why I only drew two lines of symmetry, because it only has two pairs of congruent sides. A lot of students, and hopefully you weren't guilty of this, a lot of students want to draw a line of symmetry through that diagonal, but if you recall what happens on a reflection, however far a point is from the line of reflection, that's how far it goes on the other side. So notice just this simple idea here, that this point would actually map here if I tried to fold on that line, which of course is not in fact a line of symmetry for this rectangle. So there's only two lines of symmetry for the rectangle. And then the star-like figure over here actually had 6 lines of symmetry. Created this really cool figure at the end once you got all of them drawn. So now let's turn and take a look at the last thing for this lesson. I know it's a little bit lengthier. That's because they wanted you to see lines of reflection as well as lines of symmetry on and off the coordinate plane. So item 16, if you would draw a line, I know I've said that word 1,000 times in this video, draw a line at the bottom of the page, complete item 16 before playing through. So in item 15, we saw what was known as, this is an isosceles triangle because it only had one line of symmetry, such as this half can fold perfectly on this half. And then in item 16, they tell us triangle ABC actually has 3 lines of symmetry labeled L1, L2, and L3 in the figure below. And what can you conclude about the triangle? Well, I said that triangle ABC is actually equilateral. That's the type of triangle when all 3 sides are in fact congruent. So an equilateral triangle has all 3 sides congruent to each other. And I actually wanted to explain why that was. So L1, this line of reflection, if this really is a line of symmetry, if it really is a line of symmetry, then BC has to be the same length as AC. We're seeing that if it were to fold perfectly across that line, then BC maps perfectly onto AC. Then L2, or the second line of symmetry, implies that BC is also equal to BA, because if they had to fold across this line, L2, the length of BC would have to be the same as BA, because C would in fact map to A over that line of symmetry. And then last, L3, the one right down the middle, the line of symmetry L3 implies that AB is the same length as AC. So if all these statements really are true, because those lines were in fact lines of symmetry, then the length of BA is the same as AC, which is the same as BC. And if all three sides are the same length, it is in fact equilateral. So that's the end of the lesson, or the end of where I'm going to take you on the lesson. Be sure to take care of the check your understanding as well as the lesson practice. And as always, go back to your learning targets and reevaluate your understanding of this lesson now that the lesson is over. So hopefully that made sense. Play through this video as many times, or play through the parts that are a little bit more confusing. And as always, reach out to me if you have any questions. Thanks. Hope you got a lot from it.